Hello, my name is Spencer Grant, and I'm a senior software developer here at Inference Labs. I'm here today to introduce a brand new toolkit that we just made public, and it's called DSperse. DSperse allows you to take a large AI model and slice it up into segments that are independently verifiable. And the reason this is so exciting is because previously, large AI models were not possible to verify. You couldn't create a zero-knowledge circuit from a very large LLM, for example. But using DSperse, we can slice these large models up into smaller pieces that, when run on a distributed network such as Subnet2 or Inference Network, we can actually prove in a very fast time and provide very quick and very efficient proofs of inference to end consumers. So join me on the journey as we explore some questions about DSperse and we go into exactly how it works and why it's so exciting.
Hi, I'm Dan. I am one of the leading developers for DSperse at Inference Labs. And I want to introduce you to what DSperse is and how to use it and what it means for the zkML industry. So first off, what is DSperse? DSperse is a toolkit which you can slice, analyze, circuitize, and run neural nets end to end with backends. Currently, we support Ezekiel, but we're still developing our own internal just prove. We're also looking into expanding to Jolt, Know Your zkML, as well as other backends. And when you combine it with slicing, it becomes particularly powerful. And I want to go over and show you how to use the product and how to deploy it on your own very quickly. And I'm going to start here with the README. And even before that, up top, please follow us on GitHub, Discord, Telegram, Twitter. You can read our white paper. Um, it, all the links are provided, right? So feel free to jump in. Here is our white paper. For example, it's already published as of the 9th of August. So go in, read it, and that will give you a little bit of idea of what this library actually does. But the first things first, going through the README here, we have certain commands that you can use to manipulate and modify models and to also circuitize them and run them, generate the witness. The first one is slice. Slicing a model is it's what it sounds like. We take an AI model, in this case an Onyx model, and we slice it into segments. And I'm going to go over and show you what that looks like. Compile. Compile is a few things. In terms of Ezekiel specifically, it is you generate the settings, you generate the binary, right, the compile file, and the keys as well, and also calibrate settings as well. Compile can do all of that for you. That's just with Ezekiel. As we onboard new backends, it will still be the same command, but with each backend having its own intricacies of how to go about it, it should all be compiled into this one command. Then we have run. Run is specifically in terms of Ezekiel Gen Witness. Again, other backends will have other commands for it, but this is where you actually run the inference and get the tensor results. Prove is also what it sounds like. We're going to go ahead and run the prove and verify as well. And full run at the very end is where we go ahead and run all of these commands in a single command. And I'll go ahead and demonstrate what that looks like. The README here is pretty thorough, so feel free to go through this in your own time. We do have an install script as well. This install script should, if you go ahead and pull from the GitHub repo itself, you should be able to install DSperse via this install script, and it should get you up and running. If there's any comments, any questions, feel free to reach out to us on the Discord, on GitHub, on Telegram, Twitter. We are accessible at all of these. All right, so the first command I want to jump into is slicing. What is slicing? Slicing is what it sounds like. We take a model and we split it up into segments. So I'll give you an example here. Here's an in-house model that we've developed called Do. This model has an input, runs through 3 convolutional layers, has a reshape, 2 gems fully connected, and an output of batch size 7, right? So a tensor with 7 entities inside of it. When we slice this model, it's going to get split into segments, into slices, and I'll show you what that looks like now. There we go. It sliced into 5 different segments here. So if I go ahead and look at it, the first segment is just the input and the first convolutional layer here. and ReLU output as well, right? The second segment is the ReLU output as the input, and then the convolutional layer, and it continues. The third segment has the reshape in it. The fourth segment here is the first gem, the first fully connected segment. And the last segment is the last gem as well as the output here. And we can see it's 1/7 here, so batch size 7. We've also, in this case, generated a metadata file, and you're also free to explore this file as well. What this is just basically the metadata about the model itself and the slice points of exactly where we sliced it, the segments where the segment files are, their expected input-output tensors, etc. So we've gathered all the metadata about this specific model in terms of how to run it in its segments and its slices. I'm going to go ahead and show a few more examples to make this a little bit more concrete, right? And as we know, model architectures can get quite tricky. So here's another simple one. This one is net, right? This is Lynette. Go ahead, quit that, and I'll reopen this. This one has 2 convolutionals, right, with max pools in between. It flattens out to 3 fully connected, 3 gems, right? If I go ahead and slice this one, by the way, I'm slicing here via the SDK, the code itself, but the CLI commands will produce the exact same result. We still generate the metadata file as well. We can jump into the slices, and we can see the slices metadata, right? We can see where the slice points are. And we can jump to each segment, right? So up top, we got the input, we got the convolution layer, and we go through the max pool output, right? So here's the first segment. I'm going to jump into segment 1, which is the second segment here. We start with the max pool output, right? Then we go right into the convolution, and we end with the flatten, right? So we start here as the input, go through the convolution, end with the flatten as the output. And we're going to go ahead and continue. We got the flatten output. We'll go into the gem. We'll go into the second gem as well here. And we'll go into the final gem. And then we have the output. So what we're doing here is we're literally chaining the segments, right? We're slicing the model into specific slices, into segments. And later when we run inference, we're chaining them together. And the slicing here is the tricky part, right? So what if we have a model that's a little more complex, right? So here is a model. This is ResNet. Again, another popular model. And this one has a lot of branching, right? The other two were pretty simple. They were straightforward. This one has a little bit of branching going on here, right? We start with a convolution, right? We get to a max pool, and then we start branching, right? So if we go ahead and slice this one, we can go ahead and look at the slices. And in this case, we have 21 slices. Go ahead and open the first segment. And in this first segment, you can see we have the input, we got the convolution, and we end with this max pool right where we branch, right? So I'll open the next segment here. We start off with this max pool as the input. And in this case, we're actually going to the left here, right? So we go to this convolution. And then I can open the next segment. And you can see with the next segment here, what we're doing here is we go with the max pool. And we got this ReLU output here. So with this next segment, we're combining this convolution with the input of this max pool. We go to the add and to the ReLU. And we have the output here of the ReLU as the next segment input, right? So I'll open this one here. And we continue off. Here's the ReLU. We got the convolutional layer. And then we keep going forward in this exact same manner here. And through all the branchings here, it doesn't matter which segment you pick. Through all the branchings here, we will go through and slice it up in a way to where we can go ahead and chain it and reconstruct it back together, right? So this is how the chaining part of this works. And at the very end here, if I scroll all the way down, you can see we flatten, and then there's the gem, and there's the final output as well, right? If I go to the layer right above this, we include here in this, the layer right before the last one here, where we end at the flatten, we got the global average pool, the ReLU, the add, and we got the outputs from both of these here, right? This output, right, as well as this output here. And we go through and we basically slice the model up. That's what we're doing, but it gets even trickier, right? So there are a few models out there, and I'd like to point out age as an example. And this is another model that we play with here. And this one, the complexity increases as well, as you can see here. And there's multiple outputs in this one, right? And there's multiple branches that we can go through. And so how would we slice up this model here? So let's go ahead and just run it on age here. There we go. 32 segments total, right? 32 slices total, from 0 to 31. And we can start off in the same fashion here, right? So we got the input, and in this case, we're branching to the left, right? So we got the convolution, the batch normalization, and we end over here at the average pool. And in the average pool, if you look at it, it has a branch, right? It branches off into two separate directions. And we got an output as 109 here, right? And then if I go over to segment 4, you can see that segment is actually where it branches the other way. We go from the input to the convolution to the batch normalization, the tan, and we end with this max pool here. And this max pool again branches off into two separate directions. If you're wondering, hey, what about segment 1? What happens here? We're actually going off in this direction here. And here's this convolution right here. And then we go down to batch normalization and ReLU. Did I get the right one? Convolution, I'm sorry, here's batch normalization, ReLU. Here's this specific path here. Pad and average pool. And here we branch off in two directions again, right? But we also have all of these inputs here, right? These inputs here are needed for putting it together, right? This batch normalization. These are also optimizations that we do on our side as well. So that's age. That one's a little bit more complex. And it gets even more and more complex from there, right? We've played and sliced a lot of models. This is slicing. To go take it a step further here, I'm going to go ahead and start compiling it, right? So at this point, we are actually free to run with the slices. Maybe I'll demonstrate that first. So I'm going to go into the runner here. I'm just going to run Doom, right? So the very first one, and I'm going to stick to Doom simply because it's small, and for demo purposes, it's not going to take up a lot of time. Go ahead and run it. And as you can see here, we ran it and we had an Onyx only prediction here, right? So if I go to Doom, I go into the run. We now have a run metadata as well. I can go into the run itself and look at the run result. Here's the run result, right? Predictions 2 in this case. And we got all the segments and we went through them with Onyx inference only. And we chained it together and we got the final result. Overall security here is 0. Ezekiel gen witness slices is 0. None of them went through any Ezekiel processing whatsoever, right? So I can go ahead and delete this. And what I'll do now is I'll actually go in and I'll compile the slices. So I'll come in here, there's Doom, and I'm going to go ahead and compile it. And in this case here, I want to compile the whole model itself. And not only that, I also want to provide an input file for Ezekiel specifically, and this input file we'll use to calibrate the settings. So as I go through this, I can see that for each segment here, we've already generated the calibration file. And for segment 0, the first segment here, we have the compiled model, a model.compiled file. We got the settings JSON as well. And we now also have the keys, and we're on to the next segment here, so segment 1. And we're done with segment 2 as well, and 3 and 4, and we're done. So now we have all the segments here are fully Ezekiel circuitized, right? They're circuitized, they have their settings generated, they have their keys generated. And now when we run Doom, we should be able to run it through the Ezekiel pipeline. And there we go. And we have, right? So I can go back into the run, and we can go through the run and we can see the input and output for each segment, each slice, right? And we can go into the run results here, right? Run results are extremely similar to what they were with Onyx. The predicted results the same, right? In this case, all of our slices here have went through the full Ezekiel gen settings witness generation method, right? The Ezekiel gen witness function. And we've gotten our final result, and it was all successful here. So the next step would be to prove all the slices here, right? So I'm going to go ahead and prove all the Doom slices. While the proving is going on, I can jump into, there's a file called, for each run, it's called run result JSON, right? And I can jump in and I can see, right? So here is the execution chain that happened. We started with these segments. We went down, basically down the chain. And we've gotten our final output. Also, we can go into each segment individually and get our out and read what it is as well, right? As you can see here, segment 0 proof has been generated, so the file appeared here. We can see what the inputs are, what the outputs are as well, and the proof as well. And there we go. So we have now run the full proof pipeline through this full model here. So we have the proof execution done right here. We can still see that the execution results from Gen Witness are still here. And all of these segments have went through and went through the proof, right? The Ezekiel proof. So let's go through and verify them. And this is the same idea here. I'm just going to go ahead and verify the very first Doom model here, right? And this one was much quicker, as expected. And I can go into the run results here, and I can see all of it verified successfully, right? All the segments were verified. And overall security is still good at 100%. We got individual slices that went through, and they all went through the Ezekiel pipeline in this particular case. So what else can you do with this? So I want to show a few scenarios that you can run through. And I'm going to go ahead and start that by deleting both the run and the slices themselves. And what I'm going to go ahead and do is I'm going to reslice Doom, but I'm going to take a different path. And I just want to show some of the capabilities here. We got the same slices and the same segments as we did before, but instead of going through and compiling all of the slices in all the segments, I'm just only going to compile a few layers, right? And let's say I want 3 and 4. Let's say it's the last two. I might have went through and did some fine tuning on these, right? I got, and these two are the ones where I want to obscure the weights and biases. So I can go through. And the calibration is finished. And in these two, I have now the models, right? In the previous ones, it's only the calibration JSON that's needed for this, but these have not went through the zkL pipeline, whereas segment 3 and segment 4 have. And so I'm going to go ahead and run it now. And I'm going to go ahead and run Doom. And as you can see, we still got the same predicted result here. Ezekiel gen witness on only segment 3 and segment 4, as we specified before, and Onyx inference on the first 3 segments. I can go ahead and prove. When I prove, the prover will run, in this case, much faster because the system is smart enough to understand that there's only 2 segments here, right, that need proving. The first 3 did not go through the Ezekiel pipeline. They don't have circuitized slices, but these 2 went through the gen witness are the ones that did go through the circuitized slice are circuitized. So only these 2 need proving, and the same thing with verifying. Here we go. We got 3 and 4. So this gives you a lot of flexibility in terms of how to approach zkML in general, right? You might not need your full model to be fully circuitized, and that takes a lot of resources and takes a lot of processing power. You might only need your fine tuning to be obscured, right, where your weights and biases are hidden. And in that case, you can only circuitize, for example, the last 2 segments, the last 3 segments, and still get the result that you want. And your customers can run the inference execution much, much faster. What about the last command here, right? Full run. So full run, I can switch over here to the CLI itself to demo this one in particular. I'm going to go delete these. Don't need them for this example, but I can go and disperse, right? And I am greeted with this CLI, right? And in here, I'm presented with a few options here, right? We can slice, run, prove, verify, compile. All of this is what I just went through a few moments ago. But we also have full run, right? And in this case, what you can do is you can provide your own model, right? Your own Onyx model if you want. Or you can select a built-in one, right? Doom is built in, that's our own, and there's net, which is LaNet. And in this case, I can go ahead and just run through net. So what happened here is it's going through the full pipeline. It starts with slicing the model. It created this output at this directory here where you can actually see your slices. And it went through and created, in this case, 5 slices, the same as Doom. And it's going on and it's compiling or circuitizing, Ezekiel circuitizing the slices right now. So I can jump in here, go into DSperse, and I can see net. And go into slices, and here's my slices. And there we go. So what happened here is compiling is now done, right? So it went on to the next step where it runs inference over the slices. And it found the input JSON. It ran the inference, in this case, for LaNet predictions 3, right? So 0, 1, 2, 3. And this is the maximal result here. And Ezekiel gen witness on all of them. And now we're running the proof. So while this is running the proof, if you go through our white paper, you will see that even just slicing these segments and running each one through the Ezekiel pipeline gives us drastic improvements over circuitizing and running the whole model as a whole, as one. And we're done here. And for Net and Doom specifically, these two models are mentioned in the white paper as well. Feel free to go over and see the stats of back-to-back comparisons with an Ezekiel full run versus a sliced run. In this case here, we have verified and proven all of the segments with a successful run, and you can go and look at all the data in this folder here. This gets automatically generated. We do have flags if you want to put them in specific locations or run specific models. That's all freely available to you. Thanks.
Obviously about DSpers. So my first question here is, do I need to slice every model?
Not every model. It depends on the size of the model. There are some models that are small enough where you won't need to slice them. The performance gain you'll get out of running smaller segments is actually going to be minimal compared to the size of the model. But for anything larger than a very small image classification model, it's going to be beneficial to slice because you'll be able to maximize the performance of each machine that you're running one of the slices on in order to get the most performant output.
Given the dynamic and ever-changing landscape of ZK, do you believe DSpers has the ability to stay current?
Absolutely. And the reason is really the way that it's designed. We use the Open Neural Network Exchange format for slicing up models, and we're already proof system agnostic. So currently we support both Ezekiel and a prover backend that we've been working on in-house. Now, I think that it's easy for us to adapt to new systems that come out because we have this very generalizable framework constructed for slicing up models in a consistent format. And we're already prepared to do that across 2 and more proving systems as they come out and as they prove themselves to be more performant over time.
How does using DSpers impact the accuracy of a model?
In some cases, DSperse actually increases the accuracy of the model relative to a baseline full circuitization. By optimizing for smaller circuits, we're able to preserve more accuracy. We can kind of increase the accuracy per layer and preserve that through the chain of proven circuits that run. When compared with one of the larger size circuits you would create without using DSperse, you would use accuracy as a trade-off against performance. And so you would need to decrease the accuracy to a higher degree because your performance would be astronomically high with this level of accuracy. With DSperse, we reduce that by splitting up the chunks into very small pieces. And when we do that, we can increase the accuracy on each of the pieces because the computational complexity is still going to be relatively small at the end of the day. So this allows us to preserve a higher degree of floating point precision between the individual chunks that are being proven and ultimately leads to a more accurate result.
Can DSpers run without a distributed network?
Yeah, it absolutely can, and that was part of the motivation behind open sourcing it and designing it the way we did. It's agnostic to the network that it's deployed to, whether that be an internal network, think a data center, or even just your local machine, or a network like Subnet2 or Inference Network. It can run seamlessly on any kind of network, be it a single machine or a collection of machines, however configuration works best for you. Having DSperse as a toolkit for Subnet2 is critical to the scalability of the network. Previously, some models that are larger in parameter size were out of reach, even with the amount of optimizations that miners are able to achieve. Still, even converting these models into zero-knowledge circuits is prohibitively computationally expensive. By splitting up the model into very small pieces, we can harness the full power of the network to prove in a distributed and parallelized fashion, which improves performance, but also lowers the barrier to allowing us to run these larger models at scale. And so we can support a way wider variety of models on Subnet2 and verify an increasing number of AI models over time, which is critical to adoption.